All right. Let's go ahead and get back into it. Let me do something real quick. I'm going to pull up my little video. Let's see if the video is even still active. If it decides to load up. It works. Okay. All right. You can go away. Okay. Let's talk about shear studs. Now, if you open the spec will say shear connectors. I hate that term. I will call it shear studs. I'm sorry. They call it shear connectors because they're trying to generalize and say, well, it could be shear studs, it could be channel anchors, it could be a whole bunch of stuff. But shear studs is basically the only device or connection method that's used. Now, I bring these images up just to explain some strength limit state stuff later. It will make sense here in a little bit. It would probably make more sense if I actually handed this stuff out. All right, let me pass these out. Sorry. Just getting ahead of myself, aren't I? Okay. What's this? Don't stress. All right. Now, I put these images up here to try and illustrate what's going on at the interface between the girder and the deck. Now, I'm doing this in terms of the strength limit state, and ultimately it's not going to matter, but I say this to maybe try and relate this a little bit to what you've done in advanced steel design. How many of you took advanced steel design? Did you do composite beams in there? And did you do studs, stud layouts? You did? Okay, well, a lot of the stuff you're going to see should be somewhat familiar. Ultimately, it probably won't govern, but maybe it'll at least bring up some familiar stuff. Now, I want to talk about MP, the plastic neutral axis. If the plastic neutral axis is somewhere in the girder, then this is compression, this is tension, and the force in the slab is 0.85 FC prime times the area. Sound good? Now, if it's in the slab, I propose that this force equals Fy times Ag, and you go, wait, whoa, no it doesn't. It's 0.85 FC prime times something, right? Well, I propose that C equals T. The compression has to equal tension. And if this is Fy times the area, that's got to be Fy times the area, right? So that's going to serve as a fundamental, I guess, check or a calculation in our strength limit state calculations later. Now that's pretty important for the studs in buildings, okay? So this is an image of shear studs being installed in a typical commercial steel building. So if you notice, you can see here, these are the deck pans, the stay in place metal formwork that they'll then place the concrete deck on top of. And you can see, here's the shear studs being welded on. Now, one thing that's kind of different here is they're actually shooting the shear studs right through the deck pan, okay? In bridges, we don't do that. You've got your deck pan between the girders, and the shear studs are placed directly on them. In other words, we don't lay the deck pan directly across the beams. That's for a number of reasons. We have to set deck elevations and other fatigue-related issues. But one point I'll bring out, if you look at this, these are the studs in the building, okay, in a building. And you've got, this is a given beam. You have a single stud maybe every foot, you know what I mean? Now look at this, this is a bridge. There are studs all over the place, right? There's just a sea of shear studs, okay? And the reason is fatigue, okay? In bridges, we have this issue of fatigue that we need to deal with. We just talked about it, right? Well, a shear stud, I propose, is the potential introduction of a flaw. You are welding a shear stud to the top flange. That creates a potential issue with fatigue. So hence in bridges, There's studs everywhere, okay? Make sense? Now, I do want to talk a little bit about the stud installation process, just so you have kind of an idea of what's going on. So this is an image of a typical shear stud. Now, here is the actual stud, and then this ceramic little cap on the end of it is what's called a ferrule. And during installation, that actually contains the heat input during a stud installation. Now, if you look here, see how on the end of the stud there's kind of this little nub sticking out? Okay, so here's what happens when you install a shear stud. Okay, so you have this large, it's called a stud gun that you load a stud into. Okay, and it basically conducts an electric current. You place that over the girder and you hit the trigger. Now what that does is it carries an electric current through the stud, right? Now, you all know how electricity works. Electricity is going to try and find the shortest path. It's like lightning. It tries to find the shortest path down to the ground, right? Well, this electricity is going to try and find the shortest path between the stud and the girder, so that flows through this little nub, right? So what happens is, here's the stud, shoots the electricity, it begins to melt the steel, okay? Then the electricity gets shut off, and as soon as it gets shut off, you have a nice little molten pool of steel, the stud gets shoved in. Steel cools down, melts together. Make sense? Now, I'm going to show you an installation, and I want you to kind of follow along the actual stud, and I might replay it a couple of times to give you all kind of an idea. But this is a welding machine. And so there's the stud gun. You can see there's a given stud. He's loading it in. You notice you can kind of see that little nub on the end of the stud, right? There's the ferrule that he's placing on the end. That's going to contain the heat from the installation. Now, I want you to pay attention to the stud, because what you're going to see is this. It's going to happen real quick. You're going to see the stud raise up, and then as soon as the electricity shuts off, it's going to shoot down in there. All right? It'll happen real quick, but bear with me. You see it? So, conducted the electricity, melted the steel, shoved in. Takes a little hammer, chips away. All right. Okay. Now you know how studs work. Okay. Everybody okay with that? Any questions? There you go. All right. A couple basics regarding studs. First off, one of the most common sizes of studs is a 7/8 inch diameter. It's one of the most common stud diameters that there are. 3/4 tends to show up here and there. But stud diameters, they really don't vary a whole lot, because studs that are used are a function of the stud guns that are available, okay? So they tend to go hand in hand, and 7/8 are pretty common, all right? Now, a little bit of terminology. So a stud has a certain D diameter and an H height, okay? What we're ultimately solving for in the world of stud design is the pitch, okay? In other words, we're trying to determine how far apart those studs need to be spaced along the girder. Make sense? Okay. Now, these are a couple limits which are pretty basic. There's not really a whole lot that needs to be said. It's just trying to determine that the shear studs behave the way that we intend, that they're being effective, and that they penetrate far enough into the concrete deck. So first off, the height to diameter ratio shall not be less than 4. The stud has to penetrate well enough into the concrete deck. So that's pretty basic. Number 1, the spacing of shear studs has to be somewhere between 24 inches as a maximum and 6D as the minimum. So 6D be 6 times the diameter. You know, theoretically, if you were looking at, let's say, a simply supported beam with a uniformly distributed load, the maximum shears at the supports, and in the middle of the beam there's no shear, right? Right? These are shear studs. So theoretically, in the middle of the beam, you would need no studs because there's no shear, okay? But spec says even in regions of somewhat low shear, if you're going to use a composite bridge, you need to ensure that it is composite. So you have to provide some modicum of shear studs. So you have an upper limit of 24 inches. But for the studs to be effective, you have to have a minimum limit on that as well. So somewhere between 24 inches as a maximum and 6D as a minimum. Now, there's also limits on the stud spacing transversely. Okay? Now this is a girder with 2 studs per row. You'll see here in a second, like that's 2 studs per row, and then that's 3 studs per row. You can put as many studs per row as you want, as long as they fit. Okay? You can't just start welding 8 studs on a 10-inch flange because A, good luck trying to fit them on there, and 2, you're not meeting the, or and B, you're not meeting the spec. So if S is this, you know, transverse stud spacing, it must be greater than or equal to 4 times the diameter. Okay? So that's one stud spacing requirement you must meet. The second one is that this clear edge distance has to be greater than an inch. Okay? Greater than or equal to an inch. So you can use this, these limits to say, okay, if my top flange is 18 inches wide, I could probably have 2 studs per row. I could have 3. Could I have 4? Maybe. 5? Or probably not, you know. So you can use that to help determine what amount of studs would be feasible. All right? Make sense? Pretty simple, right? Okay. All right. A couple other things. So number 1, we've got cover and we have penetration. So the cover has to be greater than or equal to 2 inches. In other words, you can't have a stud that goes all the way up to here. I mean, first off, when they start doing deck resurfacing, they're going to start cutting into studs. That's going to be an issue. And plus, there's this whole thing called corrosion. The shear stud is still made of metal, right? And metal likes to corrode. So your cover for your shear studs has to be greater than or equal to 2 inches, but you also must penetrate a certain amount into the deck for them to be effective. And usually what ends up happening is we like to place the shear stud right in the middle of the deck. So a very common length for a shear stud is either 4 inches, sometimes 6. You know, but 4 inches is a pretty common length for a shear stud. All right, does that make sense? Not too bad, right? Pretty simple. All right. All right. So when I mention studs per row, I'm going to use this term little n. So if n equals 2, I'm talking about that image on the top, 2 studs per row. 3 studs per row would be on the bottom. Now, stands to reason the more studs per row, the larger pitch I can use, and there is some truth to that. You can't say, well, I'll just use 8 studs per row and have only some at the end. No, you're going to have shear studs spaced throughout the girder. So you really just have to use a little bit of common sense and say, okay, am I providing a reasonable layout of studs, and what stud layout will produce the most economical design? Maybe try n equals 2 and see how many total studs you're welding to the girder. Then maybe try n equals 3. Then maybe try n equals 4 until you can't fit any more per row. But when you design, it's pretty straightforward. Select n and then solve for your pitch. That's it. Any questions? Don't worry, we will get into it. When we design shear stud layouts, we have 2 limit states that we have to assess: strength and fatigue. We have to assess strength because when we look at the strength limit state, you know, we're saying phi mn has to be greater than or equal to mu. Well, when we calculate, you know, mn for a composite section, we are assuming that there are enough shear studs there so we can actually reach MN for that composite section. So we got to have enough shear studs there for that to happen. And that's what happens in buildings. That's where you have, a fully composite design. Did you all do partially composite beams in steel? Did you all talk about partially composite beams in advanced steel? That's a topic in building design where we can actually say, you know what, I'm not going to provide the full amount of studs. I'm actually going to back it off a little bit, and your beam will still work. No way, shape, or form can we get away with that with bridges. Because of fatigue, it isn't going to matter. And in fact, more often than not, you can probably just ignore the strength limit state for bridges and just design based off of fatigue, and you're going to be fine. Usually you'll have to have double the amount of studs, if not triple, for fatigue. That's just a rule of thumb. Now, I'm going to go through some formulas in this presentation. A couple things. I mentioned shear connectors. I'm not talking about shear channels or anything like that. I'm talking about shear studs. So I'm only going to talk about the formulas that relate to shear studs. That's part one. Part two, you will notice that if you open up the spec and follow along with me on the spec, I have taken some of the equations and chopped them down a bit. And what I'm meaning by that is I am taking any provision that is related to a curved bridge out of the equation. It's not that it makes it harder, it's just more stuff right now, and I just want to keep it pretty basic. All right, sound good? So if you see a difference between what's in the spec and what I have here, it's because of that. All right, everybody good? Now, let's talk about fatigue, okay? First off, we have to determine whether or not we're in fatigue 1 or fatigue 2. Because we're dealing with studs and we know it's a stud, we don't have to deal with A, B prime, D, or what have you. We don't have to deal with a fatigue category. We know it's a stud. The threshold for fatigue 1 versus fatigue 2 for studs is 960 trucks per day. Usually what I do, though, is I just say, you know what, let's just go with infinite life just to keep it simple. Okay, that's usually what I do. I just keep it basic and say, let's just go with infinite life. All right. If we're dealing with infinite life, then the capacity of a stud in fatigue is 5.5 times d squared. If you're in finite life, it's actually tougher because you have to calculate this term alpha, and there's a logarithmic interpolation that has to be done, and it's a little more involved. I'd say just go with the fatigue 1 if it was me. I tend to, when it comes to fatigue, I tend to say, yeah, you've got this whole average daily traffic, and I know all the traffic engineers did all this work to do traffic counts, and I just say, I don't care, let's just go with infinite life. Don't tell the traffic engineers I said that. It's a joke, but again, not a very funny one. All right. So fatigue 1, our fatigue capacity is 5.5 d squared. Otherwise, we have to do a little more work. Now, to find the required pitch, what we're doing is finding the required pitch as a function of our shears. Okay? Now, the plug and chug expression is pretty straightforward. It's all a function of shear flow. Shear flow is a topic in mechanics. You all probably remember tau equals VQ over IB. It was one of those stress formulas you did in strength of materials. VQ over I is what's called shear flow. It's like kips per inch. And if I take VQ over I and invert it and solve, that's basically what I'm calculating out here. So to calculate the required pitch, it's pretty straightforward. The number of studs per row times the fatigue capacity times moment of inertia, short-term composite moment of inertia, divided by V sub F. V sub F is the fatigue shear range. Just like with moments, we did the moment range, this is the fatigue shear range. So if you went from positive 70 to negative 10, it'd be a shear range of 80 kips. Make sense? All right, that's the fatigue shear range. Q is the first moment of area. It's just the area of the deck times the distance from the centroid of the deck to the centroid of the whole section. That's it, just A times Y, and that'll give you Q. You can do this in Excel. It's pretty straightforward. Plug and chug. It'll give you your required spacing. I'm actually going to pull up how that works right now. So give me 1 minute. Is this? Yep. Okay. So let me pull this up real quick. So this is the set of fatigue moments for that bridge. We looked at that a little bit ago, right? Remember, we were trying to find the fatigue moment, you know, like right here for where that cross frame was. You remember that? Okay, well, those are the fatigue 1 moments. Here are the fatigue 1 shears. And you all know how to do that by now because you get your distribution factor, go through and do all that. Pretty straightforward. So here's your fatigue 1 shears. So this first point is somewhere between like 65.4, let's say, and negative 7.1. So that range is, what is that, 72.5? I do that right? Y'all see where I'm getting at? Okay. All right. Let me show you how this works. So you start off, you say, all right, here's my fatigue 1 shears. The range is from here to here. So I guess there was some rounding. Instead of being 72.5, it was 72.6. Maybe I ought to increase the decimals or something. Oh, come on. There we go. Okay. So 65.43 and 7.14, that's where that came into play. Everybody okay with that? So that's the fatigue range. For this example, I'm going to assume 3 studs per row. Okay, so all I need are 2 more quantities, I and Q. I get those from my section properties, you know, fundamental calculations that hopefully you all are pretty familiar with, right? So I is your moment of inertia, pretty straightforward. Q is just the distance. You know, look, here's what I'm doing. I'm doing the area of the slab times the distance from the centroid. Pretty straightforward, right? It's just A times D, or A times that moment arm. All right. Once you've got that, and then 5.5 times D squared, just solve for your pitch. And how am I doing that? That equation right there. Number of studs per row times fatigue capacity times moment of inertia divided by VF times Q. That's it. So you notice what's happening around the supports. Like around the supports, I get a fatigue spacing that's required that's what, like 8 inches? But out in the main body of the span, it comes out to be like 10 inches or 12 inches. It's because in the main body of the span, the shears are lower. Shears are lower, you don't need as many studs. Make sense? Everybody okay with that? Now, the first stud spacing that is required. So I'm calculating what is the required stud spacing at the very beginning of the bridge, and I'm getting 8.2. You think I'm going to tell a fabricator or a contractor to space the studs out at 8.2 inches? No. What am I going to tell them? 8 inches. So let me show you the final design so you get kind of an idea of what's going on. So here's the final design. I'll make this bigger. Okay. So the final design for this very beginning portion of the bridge, I say, you know what, let's use 8-inch spacing. And I use 8-inch spacing for a while, for about 20 feet. After about 20 feet, I look at the bridge and I say, you know what, maybe I don't need to use 8-inch spacing. Maybe around here I could say, yeah, let's bump that up. Let's use 10-inch spacing. Make sense? So it's all about just using a little bit of common sense and arranging your studs in a spacing that makes sense. As long as it's less than P max, you're good. That's it. That's really all there is to it in terms of stud design. A lot of times what you'll find is one of two things with stud spacings. Either on a simple bridge, like a 40-foot bridge, 60-foot bridge, whatever, they'll just use the same stud spacing across the whole span, just to keep it simple. If you're talking, however, about like a 160-foot bridge, 200-foot bridge, probably 2 increments of stud spacing. I mean, you could do 3, you know. There is a delicate balance between saving a couple of studs and then just making it more complicated. And think about it, if you could use the same stud spacing over and over again, you can probably install it much faster. Whereas if you're having to measure out 4 or 5 different increments of stud spacing, that's just going to make your fabricator's head spin, right? There's a delicate balance in there somewhere. I mean, if you're going to save a bunch of weight, yeah, you know, use a wider spacing there in the middle, you know. Take those studs off. But keep it simple, okay? Don't use 8.26937 inches. Just 8, 10. Keep it simple. All right? Anybody have any questions on that? Everybody good? All right. I will very quickly discuss the strength limit state, but I do want to indicate something to you right here. This is the required spacing according to fatigue. When you do the strength limit state, you get like 16 inches. See what's going on there? Strength ultimately doesn't really matter. Do you need to do your diligence and make sure that you're doing the checks? Yeah, but it's by and large not going to matter very much in the world of bridges because of fatigue. Now, to determine the I'm just going to go through this very quickly. So to design bridges or design shear stud layouts according to the strength limit state, the first thing that you have to do is figure out what is the capacity of a stud in shear, okay? And it's the minimum of 2 quantities, either FU times the area of the stud, which since with studs, usually they're made out of A608 steel, so FU is usually always 60 KSI. And the cross-sectional area, so pi d squared over 4 of the stud, right? So, you know, if it's 7/8, you know, pi over 4 times 7/8 inches squared, all right? That times the following quantity, 0.5 times the area times the square root of FC prime times EC, modulus of elasticity of the concrete. The idea is that one of 2 things is going to happen when you load a stud in shear. One of 2 things is going to happen. Either A, you fail the stud, or B, you fail the concrete. You start crushing the concrete. That's why it's a minimum of either stud capacity or essentially the deck capacity right there where the stud is. All right? Sound good? All right. Now, what we then have to do is determine, okay, there's the capacity of a stud. Now, how much force is the stud going to see? Then we divide to get the number of studs required. That's about it, okay? Now, what I'm doing here is that force that is required to be resisted by the stud goes back to that very first slide that I showed you. I'm going to even go back a little bit. The force that's going to be required to be resisted by the stud is either 0.85 FC prime times the area of the deck or Fy times the area of the girder. So if I go forward a little bit, the force that the stud has to withstand is either 0.85 FC prime times the area of the deck or Fy times the area of the girder. And that is basically it. When we look at pier regions, we tend to adjust our stud forces a little bit because the concrete's in tension, so it's not as effective. So, so there you go. All right. Then you just divide. You say, all right, here's the capacity of a stud. Here's how much load it must withstand. How many studs do we need? Like that's it. There's really not much else to say. If you go through and do the calculations, though, yeah, you can go through and do strength limit state calcs. You'll find it won't govern. Because for fatigue, You got to have studs every 8 inches, but for strength, you can go all the way to 16. So what are you going to use? You're going to use the 8. Make sense? So we assume the following stud layout. You can easily show that that meets transverse spacing and cover requirements. And there's your layout. Does that make sense? Does anybody have any questions about that? Everybody good? All right. We have one more topic left this semester. That is deck casting and survival during construction. I think we've had enough presentations on bridge failures to know that construction loads kind of matter, right? That stuff, it does seem to be important, right? So we are going to spend next week and our final week discussing construction loads. And if everything works out nicely and I have time, I'd maybe like to mention a couple things on rating and some other final topics. But that's all I got for you this week. I'm not going to assign you a homework on this, but you're going to have to do it anyways because you've got a project due, right? So just consider this a tack on to your project. We'll see you next week. Y'all have a good evening. Be safe getting home. Except for you four in the back. We got to talk. Uh-huh.